So, we continue our discussion on modeling and measurements. By the by, some people write modeling with one L. This is an American way of writing. The British way of writing is double L. So, what we have seen so far is that following geometric similarity, we consider dynamic similarity, and in the context of metallurgical processing operations, I have indicated that we can consider metallurgical processes or steel making processes to be dominated by inertial and gravitational forces in most of the situations, and therefore, we can assume that the flow phenomena or we can get dynamic similarity in steel making system on the basis of Raoult similarity criteria. And flow rate scaling criteria, which I have mentioned in the context of a gas stirred ladle system, that is Q model is equal to lambda to the power 5 by 2 into full scale. I have also indicated and talked about kinematic similarity, and I said that if there are geometric similarities between the two ladles, for example, and if the flow rates are scaled in accordance with this equation, then the corresponding time scale in the model and the full scale are going to be related in proportion to lambda to the power half. This also we have talked. Now, let us take a typical example to show you that how do you really proceed to model, for example, a gas stirred ladle system. Suppose I have, it is given that I have a ladle which is cylindrical shaped. This is the line of symmetry. So, this distance is the d full scale. Let me draw it horizontally, then it will look better. Yes. And then we have this much is L filled. So, the height of the liquid that is filled full scale. This I will say as DFS bottom, and this is DFS top, because it is a tapered vessel, and let us say that the porous plug is located somewhere here, and this distance is essentially 2/3 into RFS bottom. Let us ascribe some typical characteristics value. Let us say we talk about a 100, let this ladle be 185 ton. This is the metric ton, 1000 kg size ladle, and let me see if I can give the values. So, L filled, let us say, and this is full scale system, and I am saying this is about 3.1 meter. Then we have L full scale, which is the total height of the ladle, and suppose this is about 3.5 meter. Then we have this is let us say this is 3.1, that is better, and I think we will put it as 2.7. Okay. And then we have D bottom and we have D top, and D bottom let us put a value of 3.5 meters, and D top let us put a value of 4 meters. In the plant, most of the time the flow rate is going to be given in terms of normal meter cube. So, the gas flow rate Q full scale, which is given, and this is 1.1 into 10 raised to the power minus 2 normal meter cube per second. These are the characteristics which are given, and of course, the plug is located. So, if I have to now consider to build a model, working model, and suppose I make a decision, what are the decisions that I am going to make? I am going to make now two decisions before I go into modeling. The first decision being decision 1, which is scale factor, and let me say that I chose a scale factor, which is a very common value. This is a fairly representative value of the scale factor that researchers use in laboratories. And number 2, I make a decision about the working fluid. And let I consider that while the steel system has steel, molten steel and argon here, I consider air water system. So, my bulk liquid is water instead of steel, and as I have indicated earlier, that once we use water and that the viscosity, kinematic viscosity of water and steel are identical. So, we will not be able to respect Reynolds and Froude similarity simultaneously, and we have assumed already, or we have we will consider in general that well, phenomena in steel making systems are Froude dominated. So, in this case also that condition will hold good, and therefore, the flow rate scaling equation will, this is the flow rate scaling equation that will be used. So, now I can say that well, to have geometrical similarity, therefore, I understand this distance is redundant as far as you can see. This is called the freeboard actually. This is the freeboard. It is what is this distance is very meaningful to us, but this distance is not meaningful. So, the ladle can be the overall total dimension of the ladle that will be built in the laboratory may not have any geometrical similarity or in terms of the characteristic total length, but what is important is the depth of the liquid. So, that needs to be scaled. So, I would say that therefore, L-filled model is going to be roughly 1/3, which is the scale factor multiplied by 2.7, and that gives us 0.9 meter. So, I know that I will take a vessel, I will construct a vessel in which 90 centimeter is going to be filled up with water. So, therefore, the total height I can take it to be 1 meter, 1.1 meter, 1.2 meter. That hardly makes any difference, because this part does not take, this portion does not take part in the as far as molten steel flow is concerned. Similarly, I can say that well, d bottom, d top, by the way my m essentially represents, these are model values. So, 3.5, 1/3 of 3.5, so which is roughly about 1.23 meter, and similarly this is top, which is 4 meters. So, therefore, it is 1/3 of 4 meters, and that is going to be 1.333. We must understand now. So, the geometric features are scaled. So, plug location, two-thirds of R, which is equal to bottom. So, which is 1.233 divided by R is diameter divided by 2. So, this cancels out, and so therefore, it is roughly going to be 0.4 meters. So, that is the plug location in the model itself. From the axis of the symmetry, I will have the plug located at 41 centimeters, either on the left or on the right. It will have no consequences, because we are talking of a axisymmetric geometry. Now, as far as the gas flow rate is concerned, this is given in terms of the normal meter cube. Okay. So, therefore, this is reference to 298 Kelvin and 1 atmosphere pressure. But actually, when the gas is injected here into the molten steel is at 1600 degree centigrade. So, the volume of the gas increases quite a bit because of this temperature, and also because we have 1 atmosphere pressure it is injected at, and the pressure here is much higher than the 1 atmosphere pressure, because pressure here is going to be 1 atmosphere plus the ferrostatic head corresponding to this height when the gas is going to be released here. Okay. On the other hand, when the gas bubble is going to be here, the pressure on it is going to be 1 atmosphere plus the ferrostatic head corresponding to this particular height. So, therefore, the gas volume actually seen by molten steel is not is equal to this, but it has to be corrected taking into account the Boyle's and the Charles law. So, I would say the actual flow rate first has to be calculated, and that actual flow rate in the full scale, that will come out to be in terms of meter cube per second. And now I have, it is reference to actual state. So, I am going to say that this is reference to now 1873 Kelvin and mean hydrostatic pressure, mean pressure. Mean pressure means the pressure at the mean height. So, if this represents now my L filled by 2, L filled by 2, that is the mean height by 2, then I can say that, well, the pressure at this particular level is going to be atmospheric pressure plus the ferrostatic pressure corresponding to this. So, that is the pressure, and this is the temperature 1873, with which I am going to correct this normal meter cube. So, the expression will look like 1.1 into 10 raised to the power minus 2 into 298 1873 divided by 298, and it is inversely proportional to pressure. So, 1 divided by 1 plus rho, I take 7200 steel density, G which is 9.81, and then L filled by 2, and my L filled is equal to 2.3, it is going to be 1.35, and I have to convert this into atmosphere. So, I have to multiply this roughly by 1.1 into 10 raised to the power minus 5. So, because of this component, the gas volume is going to be increased by a factor of 6. Because of this component, it is going to be decreased by a factor of 2. So, the overall contribution of pressure and temperature is going to be, this gas flow rate will feel like approximately 3.5 times that is the gas flow rate. So, this gas flow rate needs to be scaled down in order to find out the model flow rate, because this is the actual flow rate experienced by molten steel. So, therefore, now I can say that model flow rate is equal to full scale flow rate into lambda to the power 2, and that full scale flow rate 0.1 into 10 to the power 2, but it is going to be this, and this flow rate is going to come out to be this multiplied by 0.33 into 5 by 2, which corresponds to roughly about 132 liters per minute, or approximately 2.2 into 10 raised to the power minus 4 meter cube per second. So, all the parameters now in the model have been calculated. So, I can go construct the ladle, take it 1.2 meter, fill it up with 90 centimeter of water, locate the plug at a distance of 41 centimeter from the left, and then start injecting gas at the rate of 132 liters per minute, which is going to be directed. Note that when you inject in water, water does not have a high density. So, because of pressure temperature difference, the water temperature mostly it is going to be room temperature. If it is a hot weather, maybe water temperature is going to be 26. If it is a cold day, the water temperature may be going to be 10 degrees or 12 degrees, but it is not going to be this significantly different. So, even if we are injecting the normal meter cube gas flow rate, so the normal meter cube and meter cube per second, okay, will have no consequences when water models are concerned, because of two facts, that the temperature is not very high and that the density of water is not as high as that of steel, which is 7-fold larger. So, therefore, pressure temperature correction of the flow rate in water model system are going to be insignificant. So, whatever we are injecting into the system, whether we talk it in terms of normal meter cube per minute or meter cube per minute, it does not have any bearing as far as water modeling is concerned. So, we talked about geometric similarity, we talked about dynamic similarity, and I had indicated in the beginning that when we talk of modeling of steel making system, we are concerned about the 4 different states of similarities: geometric, mechanical, and dynamic and kinematic are the parts of mechanical similarity. And now we will talk about thermal similarity. In the previous case, the systems considered were essentially isothermal. I assumed that the molten metal which is contained in the ladle, uniformly it has a temperature of 1600 degrees centigrade. Same was with my water model system, and the water was going to have a temperature of 25 degrees centigrade. So, we were talking about modeling of isothermal system. Now, when you talk of thermal similarity, obviously, we understand that we are talking about non-isothermal systems. Now, before we can satisfy thermal similarity, we must understand that we have to address mechanical similarity or dynamic similarity. Unless we can talk about the similarities of fluid motion in the system, we cannot talk about thermal similarities. So, that is why when I started talking first about modeling and measurements and outlined the 4 states of similarity, I did mention that the orders are very important. Geometric similarity, then is dynamic similarity, then is thermal similarity, because if you do not address dynamic similarity, in that case we will not be having similarities of the flow patterns or similarity of flows in the system. Now, similarity of flows is very important as far as flow of heat in the non-isothermal system is concerned, because we know that fluid heat transfer occurs from one point to another point by 3 different mechanisms: conduction, convection and radiation. And in molten steel system, convection is going to take an important part. So, unless we can talk about the similarities of the flow field, we will not be in a position to address convection. So, therefore, we have to talk, the discussion of dynamic similarity must therefore precede the discussion of thermal similarity. Heat flow depends on the convection currents generated in the system. Now, so we are talking about non-isothermal systems, and I am going to say now the statement of thermal similarity is this: temperature difference at corresponding locations and at corresponding times will always bear a fixed ratio. If such a condition is satisfied, then I am going to say that the systems are thermally similar. I define again: thermally similar systems are those in which temperature differences at corresponding location and at corresponding times are going to bear a fixed ratio. What is temperature difference? Temperature difference with respect to what? The temperature difference is with respect to any arbitrarily chosen datum. So, we can say let the room temperature be the datum, and with respect to that I am considering the temperature difference. So, I can say that the ratio of the temperature difference with respect to an arbitrarily chosen datum must be a fixed ratio, and we must understand that I am talking about corresponding location. So, once I say geometric similarity is there between the model and the full scale, I can visualize that yes, for every point in the full scale system there is a corresponding point in the model. And also we have talked about at least kinematic similarity or similarity of time scales, and I have shown that the similarity of time scales corresponds in proportion to lambda raised to the power half, particularly in those systems where flows are Froude dominated or the inertial and the gravitational forces control the flow. So, therefore, I also know that if it is 5 past 10 at model or 5 minutes after the process, initiation of the process in the full scale system, it should be maybe 1 minute after the initiation of the process in the model system. So, there has to be some correspondence between the time scale also, and as I repeat again, that at corresponding locations and at corresponding time, okay, you should be able to visualize as I say this, make this statement, the temperature difference with respect to any arbitrarily chosen datum must be a fixed ratio. Now, how can we achieve this condition? I have made this statement, but how can this condition is going to be fulfilled? That, well, I can say that temperature in the model, temperature in the full scale minus an arbitrarily chosen datum, okay, and temperature in the model at corresponding location with an arbitrarily chosen datum, okay, must be a fixed ratio. What I have to do in order to get to these results, that at corresponding location at corresponding time, this is going to be satisfied. How am I going to ensure that? The theorem is now that at corresponding location at corresponding time, if you can make this equal, that the rate of heat flow by conduction in model to rate of heat flow by conduction in full scale is equal to rate of heat flow convection in model, rate of heat flow convection in full scale is equal to rate of heat flow by radiation in model full scale, and is equal to Q generation model by Q generation full scale. And if I say this is equal to Q sub T, then I can say that yes, if this condition can be maintained, then I should be able to say that systems are thermally similar, and in that case we will see that yes, indeed the temperature profiles, temperature at corresponding location, temperature differences at corresponding location at corresponding time are going to be equal in case I have been able to successfully maintain this equality. Now, we know about these three components because heat is transferred from one point to another point by three different mechanisms. In steel making, molten steel making systems, or in vessels containing molten steel, we may not have, within the bulk, radiation may not be important. Radiation is important only from the surface, but from melt loses its temperature. What is this generation? This generation is in fact some heat evolved maybe because of chemical reactions, for example, or some heat consumed. So, the generation can be visualized in terms of a dissipation also. I did not write that. So, generation, if it is a positive generation, then that means it is produced. If it is a negative generation, that means it is going to be consumed, and this consumption of heat in the system can be because of, for example, a chemical reaction taking place in the system. So, this ratio has to be fulfilled, and then the corresponding similarity criteria can be similarity in temperature profiles can be obtained. Now, the same procedure can be followed just like the way to derive a similarity numbers. For example, as I said that what we have seen in the case of dynamic similarity, we have seen in the case of dynamic similarity that few numbers govern heat flow. For example, in the context of dynamic similarity, I have shown Euler's number, Reynolds number, Froude number. These are the numbers that control, and where from these numbers have come? These numbers have followed from two different routes. One was the governing equation I have taken, Navier-Stokes equation. If you remember, I represented it in non-dimensional form and have shown that yes, 1 over Euler is a function of Reynolds versus Froude. Then the other stream was I considered the fundamental definition of Froude of dynamic similarity, that the ratio of the forces has to be equal, and therefrom I have obtained that, well, Reynolds number must be equal to Reynolds number, Froude number is equal to. So, two different standpoints are there. From the fundamental definition, we can get the similarity criteria. From the governing equation also, we are going to get the similarity criteria. For example, if I say that look, there is a cylinder, and this cylinder, for example, is subjected to some Q, it is being heated, and I am interested to find out the temperature here, and suppose this is my full scale system, and then I have a small scale model. I want to, my objective is, this is an industrial system, I know what is the size of the cylinder, I know what are the rates at which heat is being, heated, maybe it is in a furnace, it is contained in a furnace, and it is maybe exposed to 1100 degree or 1200 degree centigrade, okay, whereby it is getting continuously heated up. So, initially the object is at room temperature, then I put it inside the furnace and the object gets heated up. I know the heat flux, I know the dimensions, I know the thermophysical properties. I want to carry out a simulation in my laboratory with a small scale miniature ingot, okay, and then on the basis of this I am going to find out that what is the temperature, which is the scaling up operation actually. So, now the question is that I can geometrically scale this down. If the L by D of this cylinder is exactly equal to the L by D, means L by D is known as the geometrical aspect ratio. If the geometrical aspect ratios are similar, in that case I can say this is geometrically similar. Now, the question is, I have kept it in an enclosure, what should be the furnace temperature? At what rate the heat should be flowing into the solid such that the temperature profile here and temperature profile here, that means this condition is satisfied between the model and the prototype. Okay. So, therefore, I can understand, now go back to say that, well, in this case heat is being transported by convection and radiation from the furnace wall into the solid, and within the solid the heat is being transported by conduction. So, I have to consider ratio of conduction to convection in the model, ratio of conduction to radiation in the model, and thereby I will be able to formulate the criteria, or alternatively I can also find these numbers from the governing equation. For example, if I consider the equation here, this is if this is an infinitely long cylinder, that means L by D ratio. The definition of an infinitely long cylinder is L by D ratio is greater than 4. Suppose this condition applies. In that case, I can assume that, well, the cylinder can be treated mathematically as an infinitely long cylinder. This is the definition of an infinitely long cylinder. Some people say 4. It is a well accepted criteria. 6 perhaps is a much more accurate criteria, but this is also reasonably accepted number as far as characterizing a cylindrical object as an infinite or non-infinite in the axial direction. So, if it is an axial, if it's a very long cylinder or an infinitely long cylinder, I can say that, well, this is basically a case of one dimensional heat conduction. The heat is flowing in the radial direction. Flow of heat along this direction is not important. Flow of heat along this direction is not important. Why not? Because the object is cylinder, so it is symmetrical for every theta. Okay, you see the scenario is absolutely identical. It is enclosed in a furnace, so it is exposed to the same surroundings. So there is a theta symmetry, and that it is infinitely long, and the consequence of infinitely long is, if z represents this direction, then this is going to be equal to 0, and the axial symmetry is this, that is equal to 0. So therefore, I am going to characterize this cylinder in terms of r, theta and z coordinate system. If these two derivatives, one along z, one along theta, is equal to 0, which essentially tells me that the transport of heat within the solid is going to be dictated by a unidimensional heat flow equation. Within the solid, what is the mechanism of heat flow? It is purely conduction. Within the solid, there is no convection, there is no radiation, it is only conduction. And now, initially the solid was at room temperature, and now progressively the temperature of the solid is increasing because it is gaining heat, receiving heat from the furnace wall. So therefore, it is a case of unsteady state heat transfer equation in one dimension. So I would say the problem, the governing equation that will characterize heat flow within the solid is going to be a unsteady one dimensional heat conduction equation in r direction or radial coordinate. And if I write that equation looks like this is the conductive transport or the diffusive transport term, and this is the unsteady state term. There is no theta direction term, there is no z direction term, because I have approximated this. Now, if I represent this equation in non-dimensional form, one can very easily do that. I have also shown you that if you take the Navier-Stokes equation in dimensional form, convert it into non-dimensional form, you get some number. And this equation will show you that, well, we have Fourier number. The temperature profile is going to be a function of that is what is going to come out to be. Okay. With respect to, I can say it is a non-dimensional equation. So, or we can write it to be is equal to. So, the non-dimensional temperature field within the object is going to be a function of the Fourier's number. This is the dimensionless number that is going to follow from this particular equation. So, the Fourier number is very, very important. So, we can understand that the non-dimensional temperature within the objects will be equal provided the dimensionless Fourier number. Fourier number all of you must be knowing from your second year transport phenomena course, and this is going to be alpha t by L square. That is what is the Fourier number. L represents the characteristic length and alpha represents the thermal diffusivity, which is nothing but K divided by rho times C. Rho is the density and C is the specific heat. So, this is the definition of Fourier number. Note that the solution from this equation depends on the governing boundary condition also. So, therefore, just by merely making this equation identical or this number identical will not give us the required result, because a differential equation without the boundary condition is meaningless. it can have an infinite number of solutions depending on what kind of a boundary condition you use. For example, we solve for our steel making systems 3-dimensional Navier-Stokes equation. You go to aerospace engineering department, they also solve Navier-Stokes equation. You go to mechanical engineering, when they solve, design turbines, flow of fluid over the turbine blade, etc., they also solve turbulent Navier-Stokes equation. You go to chemical engineering, everybody uses the same equations, but the solutions differ, and the solutions of the same set of equations depend on the geometry of the system as well as the boundary condition. So, geometry you have taken into account, governing equation give us this boundary this criteria, that the Fourier number in the model and the prototype must be identical. And now, the most important part, that we have to consider the boundary condition in order to complete the analysis. So, fortunately, in fluid flow problems or dynamic similarity, we do not have to consider the boundary condition, because if you have a wall, in the model also at wall the velocities are going to be 0, in the full scale also the velocity is going to be 0. But here at this surface and at this surface, the rate at which heat will be coming in may be completely different, because they may be enclosed in a different furnace or a different ambient atmosphere. What is the boundary condition here? The boundary condition, suppose if I assume that heat is flowing from the ambient to this purely because of radiation, then I can say that at the boundary condition, exposed boundary condition is going to be something like heat flux in the radial direction at the surface is going to be, I am making an assumption that it is going to be purely so, this is the famous expression, Stephens-Boltzmann constant, emissivity of the surface, theta infinity is the furnace temperature and theta s is the surface temperature. So, this is the radiation flux and this is the flux which is being heat flux which is being received at the surface itself. These thetas and t's are the one and the same thing, only difference is this theta is in absolute scale. So, it is 273 degree plus T infinity, that is equal to theta infinity, that is the only difference. Now, from this number also we can get a boundary condition. On the other hand, if we say that, well, it is convection, that is that controls the heat flow, it is not the radiation, but it is only convection. Alternatively, you can say that it is mixed mode, both radiation plus convection, which transports the heat. One way of saying it is totally radiation. The second limiting way of saying that it is the heat flux received at this particular point is going to be the convective heat flux, in which H is the convective heat transfer coefficient. So, if I assume that, in that case I can show that if the heat flux is due to convection, then I will say this will give rise to by K as a number which is the, and this is K solid, this is K solid, and this is, we have Fourier number, this is equal to alpha T by L square. So, this will tell us that the dimensionless temperature, okay, T over some value here, T naught I have written, is going to be a function of HL by Ks, which is the heat transfer coefficient characteristic length. What is the characteristic length? In this case, maybe the radius of the diameter, and Ks essentially represents the thermal conductivity of the solid under consideration. So, if I now say that, well, look, if this number bio number in the model is exactly equal to bio number in the full scale system, if Fourier number in the model is identical between the model and the prototype system, in that case what we are going to see? We are going to see that this condition is going to be fulfilled. Note that this number essentially represents the heat transport by conduction, convection to conduction. So, I am taking into account convection. So, fundamentally this number would have been derived by taking the ratio of the conductive to convective heat transfer in the model without considering the boundary equation whatsoever. Similarly, this number tells us the heat flow because of heat conduction only. So, we could have gotten this number by taking into account the equivalence of the conductive heat transfer rates between the two systems itself. So, the analysis tells us that thermal similarity between these two cylinders can be obtained provided this number and this number is going to be maintained. So, therefore, based on this number I will find out that what is the H that is required. Based on this number I will find out that what is the corresponding time equivalence between the two, and then it will tell that if such heat transfer coefficient be applied in this particular system, then at this particular time this condition is going to be valid. So, when such a problem is to be investigated, we must understand that we are talking here about geometric similarity, and straightforward we will talk about thermal similarity. In this case, because the domain we are trying to get thermal similarity between this and that these two objects are solid. So, therefore, there is no question of any fluid movement. So, therefore, the dynamic similarity does not come into the picture. So, the geometric and thermal similarity will entirely govern the problem, and I have shown you that, well, if n Fourier model is equal to n Fourier full scale and n bio model is equal to n bio full scale, in that case this particular condition is going to be maintained in the two. Now, therefore, I can say that, look, the bio number equivalence gives us to adjust that H model by H full scale is equal to L model by L full scale, and then we have K solid model and K solid full scale. This term LFS by LM is actually lambda raised to the power minus 1. This is the scale factor that we have already decided when we were talking about the geometric similarity, that we have maintained same L by D. So, we have L by D model is equal to L by D full scale. That is the geometric similarity, and once we have done it, the scale factor is known. So, lambda is known to us. This may be a steel cylinder, this may be an aluminum cylinder or a copper cylinder, does not matter. There is no requirement that it has to be steel. I can use a different material. So, I know the ratio of the thermal conductivities of the two solids. If I have the steel, solid which is steel in full scale system, I know the thermal conductivity of steel. If I have taken copper, I know the thermal conductivity of copper. So, this term is known, this term is known. The heat transfer coefficient in the full scale, that means the container, the furnace in which it is there. So, I know the heat transfer coefficient already in the furnace, and now I have to find out the corresponding heat transfer coefficient. So, therefore, this particular expression will give me that, well, look, H model is equal to some constant beta into H sub Fs, in which beta is nothing but lambda inverse multiplied by Ksm divided by Kfs. So, having known the value of the heat transfer coefficient in the full scale system, I should be able to adjust my heat transfer coefficient in the system in such a manner that this condition is going to be maintained. Similarly, the Fourier number equivalence will tell me that, look, I have T model by T full scale, that is going to be alpha model, alpha full scale. So, alpha T and then L square. So, this is going to be L model square and L full scale square, which is equal to lambda square into some constant, maybe beta prime. Thermal conductivity, this is K divided by rho C. So, these are material dependent properties, thermal diffusivity. So, once we have fixed the material, because what are the two steps? I said the first step is decide on the scale factor, second is decide on the material. So, the moment you have decided on this particular material, this parameter alpha fs has become fixed. You know alpha m has become fixed. You know alpha fs already what is the material in a full scale system. So, this parameter is also known. So, therefore, so now you can say that the corresponding time, so Tfs into say lambda square. So, therefore, if time from t is equal to 0, again when you talk of time in the full scale, that means you choose an arbitrary datum. So, the point at t is equal to 0, you have 0 plus, you insert the sample into the furnace. So, from that point onwards, if you say after 10 seconds, okay, in that case you put 10 seconds here and then find out what is the value of alpha square and beta prime, and then find out that what is the corresponding time, and this will be also with the reference to the point at which you insert the sample in the laboratory scale furnace. So, this will tell you the correspondence between the time scales. This gives you the correspondence between the. So, if we select the material, if we select the scale factor, then first job is to ensure that only the heat transfer coefficient has to be in accordance with this equation, and once heat transfer coefficient is in accordance with this equation, I can map the temperature here at different times and then say that corresponding to this time, if this is the temperature measured here, the corresponding temperature in the full scale system is going to be such and such, which will be on the basis of a time scale governed by the Fourier number equality. So, therefore, when you talk of heat transfer thermal similarity, we must understand that we will not only talk about the governing equation, or we will not try to derive the similarity criteria based on the governing equation, but we will have to consider the boundary conditions as well. Now, if you look at, for example, take a practical case, this is a very simplified scenario. If you take of heat flow in a tun dish, for example, a single strand tun dish, I am showing it very, okay, and I want to find out, I want to carry out a laboratory scale model. I have chosen a scale factor. I want to do the experiment with water, for example, and suppose I have made a glass vessel, tun dish shaped, and I wish to carry out experiment. I want to see the flow pattern also, but I want to consider non-isothermal flow. Now, in this case, although I can scale down on the basis of the governing equations, get the numbers and maintain the equivalence, it will be very difficult for me to maintain the equality which will come out on the basis of the boundary conditions. Because you can imagine that if you have a 1600 degree molten metal in a vessel, tun dish, you have some finite amount of heat loss. Now, water I can only use up to 100 degree centigrade or 95 degree centigrade. And at 95 degree centigrade, if I use a glass vessel, I will see that the rate at which the heat will be lost, that similarity I will not be able to maintain with the actual steel making system in the shop floor, because there the rate of heat flow is going to be significantly larger. So, it will be very difficult for us to maintain the similarity of heat loss behavior in laboratory scale system by using a glass vessel of ladle or tun dish or mold, etc. So, thermal similarity studies are going to be really difficult. Now, for example, if I consider the boundary condition and the governing equations together, I find out that, well, if this phenomena, now this is there is a geometric similarity, there is going to be dynamic similarity, there is going to be thermal similarity, because we are talking about non-isothermal system, and because the tun dish, there is going to be some fluid flow involved. So, therefore, as I have mentioned repeatedly, that before we can talk about thermal similarity, we have to talk about dynamic similarity. So, we will talk about dynamic similarity and then we will talk about thermal similarity. So, geometrical dynamic similarity essentially in this case is going to be the same number. So, it is the Froude number equivalence. Froude model must be equal to Froude prototype full scale, and therefore, on the basis of this, what is Froude number? We have seen UC square by GL model is equal to UC square by GL full scale. If I consider the characteristic velocity as this particular velocity, and what is the velocity? velocity is nothing but volumetric flow rate by cross sectional area. Okay. So, I take the volumetric flow rate Q inlet divided by the cross sectional area of the nozzle, then I get what? I get a velocity, and that velocity I can ascribe it to be equal to QC. In this case, the meaningful length scale is actually the depth of the liquid which governs the flow rate out of the tun dish under steady state condition. Okay. It is not the orifice dimension, but it is the depth of the liquid which is H which controls. So, I can say that on the basis of this we can write down Q by area nozzle divided by GH in model, and Q represents what? Q represents the volumetric flow rate, and therefore, I can say this is going to be equal to Q divided by A GH in full scale. Now, area model by area full scale is lambda square. H model by H is equal to, so this is, you can see here it is UC square. So, 1 UC is equal to Q by A. So, this is going to be actually Q square by area square, okay, Q square by area square. So, what is Q? Q is equal to volumetric flow rate into cross sectional area is equal to velocity. So, we have meter cube per second, no, it is sorry, Q is equal to volumetric flow rate into, so we have velocity is meters per second, and this is meter square. So, this gets us to, so therefore, we can say V square has a dimension. So, this is the equality of dimension, that means dimensionally V square is equal to Q square by A square, and that is what I have basically written, that UC square is equal to Q square by A square. So, A square model divided by A square full scale is equal to lambda to the power 4, H model by H full scale is equal to lambda to the power 1, and that it is equal to 2. So, therefore, I can say this equation will follow very easily, that Q model is equal to lambda to the power 5 by 2 into Q full scale. So, that means again you see this 5 by 2 correspondence comes, and the 5 by 2 correspondence essentially comes from the definition of Froude number, which tells us that U model is equal to lambda to the power half into U full scale. So, the velocities in two systems which are dominated by Froude number varies in proportion to lambda to the power half. So, the consequence of this is the 5 by 2 relationship, which we have also seen earlier. So, when we talk of tun dish, so therefore, to maintain dynamic similarity, we can say that, well, the model, if I know the full scale flow rate 3 tons per minute, I should be able to find out that what is the corresponding model flow rate in terms of the scale factor itself. So, this is on the basis of the dynamic similarity. So, we have considered the Navier-Stokes equation, and this is the limiting form because we have ignored Reynolds number. Now, we have to consider no boundary condition for Navier-Stokes equation, because boundary conditions are all alike in the full scale in the model system. So, to derive the thermal similarity criteria, now I visit the thermal equation, and also I know that with the thermal equation, thermal balance equation, I have to consider the boundary conditions. Now, the thermal similarity tells us that this condition, I am not going to derive this, is beyond the scope of discussion here. So, this is going to follow from the governing heat flow equation, which is applicable to the flow of liquid in the tun dish. So, the condition 2, and this is condition 1, and condition 3, which will come out from the boundary analysis of the similarity of the boundary condition, is that Q model is equal to 0.4 into Q scale, in which Q represents the rate at which heat is being lost from all the surfaces of the melt itself. So, this condition, only when these 3 conditions are simultaneously satisfied, we can say that yes, the model tun dish that we have fabricated in the laboratory will exhibit not only geometric similarity, but also simultaneously dynamic and thermal similarity. Now, as I mentioned, so therefore, you imagine typically in industrial surfaces, we can have 5 to 10 kilowatt per meter square as the heat flux. So, if it is 10 kilowatt per meter square, in that case, what we require in the model is going to be 4 kilowatt per meter square, and if I have a glass vessel and 100 degree centigrade temperature of water, I cannot get 4 kilowatt going out of the melt itself, going out of the liquid water bath through the glass vessel itself. So, this condition can be satisfied. What is beta? The coefficient of volume expansion, and delta T again is a differential temperature, bath temperature may be with respect to the inlet temperature. This difference may be the delta T. You can assume the the difference with respect to any arbitrarily chosen reference temperature. The reference temperature may be the inlet temperature. You may choose wall temperature or ambient temperature, whatever you are convenient with. So, this condition can be fulfilled because beta in steel and beta in water are going to be known to us. So, if we know the delta T value in the case of steel, we should be able to find out that what should be the corresponding delta T, because we are trying to find out the fluid is coming here. Why is the issue of thermal similarity coming here? Because steel is coming here at 1600 degrees centigrade. The temperature of steel within the tun dish, the temperature of steel within the tun dish is going to change significantly because lot of heat are going to go out of the tun dish through the tun dish wall itself. So, that is why the non-isothermality comes into the picture, because of continuous loss of heat from the molten metal. Okay? And therefore, the metal comes here at 1600 degrees centigrade, but it does not go out through the strand at 1600 degrees centigrade, it goes out at a relatively lower temperature. There is a temperature gradient in the system. So, that is why we want to find out that we want to study that differential temperature or non-isothermal behavior. So, we are also going to use a vessel in which we are going to put in water at 95 degrees centigrade, but then there has to be some kind of a heat loss also in order to replicate the exact behavior of steel flow in the tun dish system. And therefore, we consider the governing equations of fluid flow to get to the dynamic similarity criteria. We consider the governing equation of heat flow to get to the thermal similarity criteria, and with the thermal similarity governing equation, we also consider the boundary conditions of thermal similarity. So, three set of numbers comes out from the analysis. So, on top of geometrical similarity, we derive this on the basis of our assumption that the flow phenomena is governed by the Navier-Stokes equation and it is Froude dominated. This is from the thermal similarity, this is from the boundary condition, and as I have mentioned that this condition can be fulfilled, this condition can be fulfilled in the laboratory scale model very easily, but using a transparent glass vessel and water as the liquid, there will be no scope to fulfill. So, therefore, thermal similarity studies of steel making systems in laboratory scale modeling is going to be really difficult. And how do you get out of this then? How do you investigate process? So, as I will discuss later on, in such problems where there is lot of uncertainty in investigating a process, we resort to mathematical modeling, and then we solve the steel making problem or address steel making problem, get some numbers, scientifically visualize those. We may not physically observe them, but we can certainly scientifically observe them, observe the numbers, and then conclude that at which point temperature is more, which point temperature is less, and so on. So, wherever physical modeling is not going to be appropriate or accurate, in that case we have an alternative way, and that is mathematical modeling that we are going to do. Now, the last state of similarity that we talk about in addition to geometric, and then we have here, which you did not consider in this problem, is the dynamic similarity. And the last state of similarity is what is known as the chemical similarity. I have to briefly mention you before I conclude the discussion, particularly on the states of similarity. It is a pretty exhaustive discussion really I have given, and you should be able to understand the potential of physical modeling and some of its limitation, and appreciate the beauty of the subject, because if I do not give you a sufficient background, maybe you will not be able to see, our lecture is not going to be meaningful to you. So, these are the 4 states of similarity actually, 1, 2, 3 and 4, and we have talked about the 3, and the last, if I wish to make a few points on chemical similarity. Now, when we talk of thermal similarity, we talk of temperature, heat flow similarity. When we talk of dynamic similarity, we talk of flow similarities, and we talk of chemical similarity. That means we are talking about similarities in concentration profiles. Now, chemical similarity comes into the picture because our systems may be reacting systems. Why? Maybe they are all reacting systems indeed. Okay, we have carbon oxygen reaction, we have desulfurization reaction, and so on. So we would like to simulate, therefore, in physical modeling chemical similarity to get similarities in concentration profiles of a particular species. Now, just like the species transport is like heat transport, okay. Heat is also energy, so it's a scalar quantity. Flux is a vector quantity. Heat is a scalar quantity. So the species transport or mass fraction of species which is moving from one place to another place is also a scalar. So the same type of argument is going to hold good in the case of chemical similarity also. So I will say now, see, remember the definition that I gave you in terms of thermal similarity. I will map a one-to-one definition for chemical similarity also. Chemically similar are those systems where, in place of temperature, I am going to say where concentration difference with respect to an arbitrarily chosen datum maintained a fixed ratio at corresponding locations and at corresponding time. So replace that word of temperature by concentration, whatever I have defined, replace these T's by concentrations or mass fractions, you will get the conditions, the results of the chemical similarity. And now these are the reasons why heat was transported from one point to another point. What are the corresponding mechanism? Mass transport by diffusion in the model to diffusion in the full scale, mass transport by convection in the model to convection in the diffusion, convection in the full scale. Radiation does not take place in the case of a system. There may be mass generation or depletion because of chemical reaction. So by knowing thermal similarity, if you know thermal similarity and if you understand the definition, you can immediately formulate the definition of or the criteria for chemical similarity.